Hello, Professor. My name is Michael Awamistiawan. Today, I'm going to present to you the midterm presentation that you have assigned to us. The title will be the Thermodynamics on Mechanoluminescence. Mechanoluminescence is the research that I'm currently working on. As you have assigned, we are going to discuss more about each of our individual research. So I will discuss the mechanoluminescence and also the derivatives of how thermodynamics correlations occurs in my research. Now, without further ado, let us continue to the presentation. First, before delving into the research, I want to give a few clear message or definition about mechanoluminescence, or uh, another term that you might see or read in the journals is that piezoluminescence. Virtually both means the same. Well, the definition itself that the material can emit cold light when it receives mechanical stimuli. Cold light. There is so non-thermal. And then there are a few types of mechaniluminescence. One of the first one being fractaluminescence, the first discovered phenomenon. What we are going to focus on is the elastoluminescence because fractaluminescence we can see in almost all of the crystalline materials or 50% of the crystalline materials. There's a lot. And 36% of the inorganic solids. That's quite a lot, but fractaluminescence is not quite applicable since it is only like one time luminescence, and we have to reconstruct it again, or we it requires new material and so on. So what we are going to focus on is this elastical luminescence. Now, after the definition, I will delve into a brief history background of mechaniluminescence. So the first discovered mechaniluminescence, or we will call it fractaluminescence, it is in 1650 in one of the scientific journals, and then in 1999 it started to gaining traction because it is the discovery of first elastical luminescence of strontium aluminate doped with europium doped with europium. And then it started to grow after that. The the research and also applications. The research shows that it has a growing number of different materials that researchers have found and also possess this elastical luminescence that we can utilize for a much better applications. And then now we we will develop a research field on mechaniluminescence, a few models of mechaniluminescence and wider applications with increased intensity, because intensity was quite a problem of mechaniluminescence itself, since low intensity won't be extensively used for all applications. Now, after the history, how does it work? That's the main question. That's the main question, right? Uh, So, mechanical the important points here is that it is closely related with the trapping of electron and trapping of electrons. So, the trapping itself is the features of elastical that enable the material to be to possess persistent luminescence without breaking it. And then it is important for us to know the trap depth and quantify it in order to optimize its properties. This is the thermodynamics correlation that we are going to talk about. But on the left hand side, you can see here the red one is the doping or the luminescent center, and then the luminescent centers, because it is a doping, it has vacancies. This vacancies, this little dot, little black dot, represents the electron that is trapped, and then will be detrapped and trapped through the stimuli of this uh, piezo stimuli, or we can call it mechanical stimuli. The role of dopant is quite critical since it will affect the even the luminescence color of the material. You can see here uh, the luminescence that it possesses in a sample. It is shown here in the source that it can have like this reddish, quite high intensity, especially in the dark room. Then what is my research? My research is this creating new magnetoluminescence material. Uh, what we are what we are what YLab or we are trying to do is that we will couple this elasticoluminescent material with magnetostrictive material, and then we can convert this magnetic stimuli into cold light emission via the deformation of magnetostrictive, and then will be converted to elasticoluminescence as a cold light emission, thus reducing the loss from this electricity conversion. It is quite a similar concept to MME or magnetomechanoelectric generator that FMDL or our lab has created. The magnetoluminescence will be able to provide light without any conversion to electrical energy. So it will be quite efficient and also provide luminescence. However, the problem lies on how to synthesize and characterize the elastical luminescent materials, because apparently our lab is not quite adept or expert at this elastical luminescence field, but we have been quite an expert on the magnetostrictive material and also cantilever structure. This is the energy the energy transition uh, from the formerly usually we convert magnetic strain and then electric, then we convert it maybe to an LED through to get luminescence, but now we can just go from magnetic strain and then luminescence, a much more uh, much more much less conversion, which means better efficiency. Then how would we correlate it with the thermodynamics approach that you were assigning to us? The correlation is quite apparent, as you can see here, that the thermoluminescence are used for this trap depth identification. I previously mentioned that trap depth identification is important because trap depth is what causing this luminescence uh, phenomenon. You can see that in the left hand side, one of the previous research that I've already discussed thoroughly is that they are doing this thermoluminescence to identify the trap depth based on the peaks that the material show, the intensity peaks. There are two intensity peaks. It is signified by the co-doping that the material is doped by the researchers. In this paper, they are using the Hugin-Stratton method to quantify the electron depth caused by the doping. There are two because there are two dopings that the research used, and then the Hugin-Stratton method utilized the peaks seen in the left-hand side of the graph, and it includes the mathematical expression that we will derive in the next slide. Now, this is the equation that we will try to derive from the Huygens-Stratton. First, you can see here in the equation A, this is the general equation governing the behavior of glow curves. The glow curves is the previous curve that we are discussing, and then we know that I is the glow that's intensity in the equation A, and then L is the order of the kinetics, S is the pre-exponential constant, L equals 1, then S is identical with frequency factor. Assuming the heating rate beta is constant, uh, if we if we know that the heating rate is constant, the equation B will be achieved. And then equating the derivative in equation B, the condition for maximum is found to be equation C. If we use the derivatives in the equation B, we will get this equation C here, derivatives and then C. Well, on the other hand, we can solve it E, but we can solve this. We can already solve this, but we required E and also S to solve E. We required this value. However, some researchers are suggesting the use of two heating rates that are able to solve both E and S through the process of elimination. That is what basically Huygens-Stratton are proposing. Huygens-Stratton are proposing not only two but several different heating rates. Uh, in the research that we have discussed, last week, is that the research are using three different heating rates. Three different heating rates uh, to and then plot it with this natural logarithm Tm power of 2 divided by beta or beta the heating rate versus 1 over the temperature, I will say the gas temperature material, which is in the following question will yield a straight line. This straight line, if we can calculate the slope itself is the trap depth, is the value of the trap depth. That is how we quantify the trap depth to the Huygens-Stratton method. Quite interesting because it is a very mathematical approach and requires the thermodynamics approach that we have been discussing. Then what is the what is the methods that we can adopt in this research is that we can use this Huygens-Stratton method to quantify trap depths in the synthesized piezoluminescence. It is quite important because identifying this trap depths enable us to understand more about the luminescence properties and how the amount of the trap depth or the depth of the trap depth is affecting the maybe luminescence intensity or even the color of the luminescence itself. And then by calculating the trap depth, we can study and validate the effect of dopant variations. We can use different dopants and experimenting on how this dopants creates this much depth in the trap depth and so on. In conclusion, this thermodynamics approach is important to identify and quantify trap depths or depth traps. It is important to identify and quantify trap depths and it can show which materials are necessary and which materials are not. So we can use this as a dopant or maybe this as a base to know whether this will be a good mechanical materials by experimenting thermoluminescence on it and then assessing its glow curves, thus identifying its strap depths. If it does not possess any, we know that it is not a good or even maybe does not possess a mechanical properties. And then, as I have already mentioned, that the quantifying of trap depths will enable our understanding further how the difference the, of those can affect the luminescent properties. And then thermodynamics and mathematical approach for identifying trap depths from thermoluminescence curves proves to be consistent and validated with the different sets of experiments that we have already discussed on how to derive it from the general equation to the Huygens-Stater method assumption. That is all for my presentation. This is the reference that I'm using. If there is any question or any feedback or remarks, please you can reach out to me through my email and or maybe through my other contacts that you might find. Thank you, Professor, and goodbye.